Hello and welcome back. In this week, we're going to look at feed-forward neural networks. So last week we looked at linear regression, and we'll continue with the discussions and to see the need for the motivation for neural networks, and then go on to describe the operations in a feed-forward neural network. Okay, so we saw that linear regression. We modeled the output y. We denoted the output of the model as y hat, and we said y hat is w transpose x, where w is the vector of weights and or the parameters of the model, and x is the input. Okay, so x is actually again a vector, so x has its own components small, so x would be a particular x would be x1, x2 up to xn features. So each one of them, these are called features, so there's n features, and we had a bunch of these training vectors along with their output. So for each of these x's, capital X's, there is a corresponding y which was also given, and we used that to estimate the parameters w, unknown parameters w, through gradient descent. Okay, this is what we saw last week. Okay, but you will see that this function, this linear model, so basically this f of x as we call it, is inadequate for a lot of the real world data. Okay, so we're going to look at one example, which is basically the XOR gate or the exclusive OR gate. So very simple toy example, and we'll see a lot of things, learn from a lot of things from there. So why would I say that this function is not good for a lot of real world data? Because a lot of real world data has a lot more features. Okay, and sometimes the relationship between the correlation between the features and the outcome y or the output y is not known a lot of times. Okay, and also the dimensionality of the data is an issue. So for instance, let's say we have a picture, we are trying to label that picture as belonging to, let's say, a particular class. So for instance, if you have a chest x-ray and you want to say if it's a normal or an abnormal chest x-ray, so a chest x-ray, a digitized chest x-ray would be of the size 1000 cross 1000, so which gives rise to 10 raised to 6 features, right? Like, so this is x1, x2, xn up to x 10 raised to 6. So with something like that, having a linear model might not be a very suitable thing, right? And we'll also see that maybe the outcomes are not exactly linear, right? So better model would be a non-linear combination of the input vectors. So something like this, where we still have, this is still linear, right? Because it's still w transpose, but instead of x, we have phi of x. This is some non-linear combination of x's. Okay. So for instance, if you have x1, x2, so you will also have x1, x2, x1 square, x2 square, and other combination x1 square, x2, so on and so forth. You can keep going like this. Okay. So then, of course, the problem is how do we estimate phi of x? So that we can do something like what I did here is to write down a lot of possible functions and then use that to fit the model, right? And another version is if you study the problem. So for instance, we are talking about chest x-ray, right? And we now know, how to make phi of x. We now look at the picture and then identify some aspects or some properties of that image. Let's say chest x-ray, if it looks very bright, we say, okay, that's a feature. Okay. So we extract these features, quote unquote, these hand engineered features. That would be the phi of x. Okay. Or the size of the anomaly, right? So that's what we will be looking at as far as chest x-rays are concerned. So we can either write this down like I did here, or we can handcraft by observing your data and figuring out some functions which will serve as features and has a good linear relationship to the output. Or we can learn phi of x. So this is where neural networks come in because they help you learn. So neural networks here. You can learn this by modeling f of x using a certain structure, right? So basically it's a composition of functions. We'll see that later. So by modeling this in a different way, we can actually learn these features, and this is where neural networks make a big difference. In terms of if you compare it with other machine learning techniques. Okay, so let's take a look at this XOR model, that learning XOR problem. So XOR is an exclusive OR, it's a logic gate. So it usually it has two inputs, x1 and x2, and a corresponding output. So in the case of XOR, these are the there are only four combinations possible because x1 and x2 are either 0 and 1. So this is the real toy example because there is no such thing as test data. What we are trying to do is just try to fit the training data. So now if you look at this, 0 0 will give output 0, 0 1 and 1 0 will give outputs 1, and 1 comma 1 will give you output 0. Okay, which is what is plotted here. So this x horizontal axis is x1 and the vertical axis is x2. So now we have these 4 points plotted. So now what are we trying to do here? Okay, so let's treat this like a classification problem. Okay, so the only way we could classify this is to find this curve. I'm going to draw one hand drawn curve. Let's say if you find this curve, let's say this is a curve, this region encompassed by the equation of this curve, right? If you find it, then we can say everything inside this region is 1, everything outside is 0. Okay, so I'm going to wipe this out just for make this much more clear. On the other hand, if you see, we cannot draw any line. There is no line possible or plane possible which can divide this into two regions. One side is all ones, the other side is all zeros, right? It's not possible to draw a straight line. In other words, if you are doing a model y hat is w0 plus w1 x1 plus w2 x2, then this simply will not work. Okay, the reasons are here right there. So for if you consider x1 equal to 0, then the output y is increases as x2 increases. When x1 is equal to 1, the output y decreases as x2 increases. So which is not possible to be, that kind of behavior cannot be captured with just this parameter w2 by tweaking one parameter, right? So that becomes a difficult problem to solve. So the only way we can do that is to do that curve I showed you, right? So this kind of problem is not linearly separable, okay? It's not linearly separable. So basically we cannot do this model and hope to find, hope to fit this data, okay? So then what kind of things will work? Okay, let's look at that further. So if you look at the output of XOR, then we can actually rewrite it in this form. x1 plus x2 minus 2x1 x2, where we are actually treating it like numbers, like this is an algebraic formula, okay? You can plug in 0, 1 and see that it works. You can also write it in this form, x1 minus absolute value of x1 minus x2. You can see that both of these formulations are nonlinear in x, in the features, or nonlinear in the features, and if we use this kind of function, then we can actually fit by using a linear model. When I say linear model, I am talking something like W transpose times phi of x. So for instance, how do we do that? Let's look at this. So what I mean is y is w0 plus w1 x1 plus w2 x2 plus w3 x1 x2. Now this model will fit y. So this is y hat will fit y. So the truth table will be able to guarantee for, we can estimate w's, the w0, w1, w2, w3 for some value. We already know the value, right? W1 is, this is 0, W1 is 1, W2 is 1, W3 is minus 2. Okay. So this is what we have seen. So using this model we can fit. So what we have, this is the case where we have y hat is W transpose phi of x, where phi of x just turns out to be this collection x1, x2 and x1, x2. Now once again we go back to the image example where we have chest x-rays. Okay. So let's just do a toy chest x-ray, right? Now each of these individual pixels in a chest x-ray are the xi's, small xi's, right? Now in a 1000 cross 1000 image, digitized image, we have 10 raised to 6 such pixels. So we have 10 raised to 6 features to begin with, and then in order to be able to construct, imagine how many we have, the combinations we can do, how many x1, xi, xj, and then we can also do xj, xj, xk, so on and so forth. So this is an explosion of features. If you do it this way, an explosion of features, and that becomes very hard to manage in both in terms of memory and computation. So in some cases where we know such expressions are possible and we know that it's easy to write down by hand, or maybe it's not, maybe it's only hundreds of features rather than thousands of features or millions of features, this is probably a very good model to use. But it will be nice if there's another way of doing this, right? The other way of doing this is to have more layers of computations, okay? And let's see what we mean by that just using this example. Okay, so we'll now look at what we mean by different layers of computations. So you can implement an XOR gate as in this form as x1 or x2 as an OR gate plus x2. This is a OR, x1 dot x2. This is an and this bar is a complement or a NOT gate, if you can think of. Okay. So we are now computing two intermediate features. I am calling them H1 and H2. Call this H1 and this is H2. Okay. And when we compute these two intermediate features, we will see now upon computation of these intermediate features, the problem becomes linearly separable. So I will just draw that in there and then so that you can see, and then we'll also look at these computations in a different way, like in the form of a network of computations with different layers of computation, and then we'll see why we call it intermediate computations, etc. So if you plot this image, we plot this not the image, I meant the graph of, in this case this is H1, this is H2. So if you look, these 2 points 0, 1 and 1, 0 for x1 and x2 respectively has now collapsed to 1 point, 1 comma 1. So, okay. So if H1 is 1 and H2 is 1, the output is 1. Okay. So I'm going to indicate it with a solid dot. Okay. And if you look at the other options you have, right? If for 0, 0 you get 0. Okay. I'm going to put 0, 0 here. I could have put it at the corner, but let's just put 0, 0 here. And for if I have, let's say, this is for H1, H2. So 1, 0, 0, 1 is also 0. Okay, so I think I made a mistake. Sorry. Let me just wipe this out. So we are looking at H1 and H2. So what I have plotted here is 1, 1 is 1. That's fine. And if you look at 0, 1, it's also 0. So 0, 1, 0 is one type of output. And if you look at 1, 0, that's also 0. Okay. So now it's linearly separable because you can always draw this line. Of course, there is a whole bunch of lines you can draw here. So that's another issue there. But we can have a line which will split this into two regions depending on the value of H1 and H2, which will give you, the correct answer, right? So if you are H1 is 1 and H2 is 1, it will fall automatically in this line, this side. If for all other values, it will be there. That it is able to do that because by doing this intermediate computation, I have collapsed both 0, 1 and 1, 0 into the same numbers, right? 1, 1 and 1, 1. So these two got collapsed into 1 point. So then I can now draw this line to split that, correct? Of course, now the problem is, because you can draw like a bunch of lines which will do that, but now the problem is linearly separate. Okay. Now, what do we mean by intermediate, computations? What do you mean by layers of feed forward layers of computations? That's what we will look at in the next. Okay, so now we will look at what I meant by the intermediate layers of calculations, right? So we saw that in the previous slide where we see where if we split it into a set of two different Boolean operations, then we got the problem to become linearly separable in terms of the new variables we calculated, right? We calculated these new variables H1, Boolean variables H1 and H2. So I'm just going to illustrate that in terms of a graph so that now we can go on to make connections about how neural networks work. Remember, all the operations I am showing here are actually Boolean operations, not algebraic operations. Okay, so Boolean operations. So let's look at x1 is an input. Okay, x2 is an input. Okay, and we connect this to another computation. Okay, we call that one second, we call that the h1, which is x1 or x2. Okay, then we do another connection to another computational unit where you compute h2, which is x1 and x2 complement. Of course, we can always take these two output from here and connect it to one more box where we do h1 and h2, and that output is your y hat. Okay. So this intermediate layer of computation is what enabled our problem to become linearly separable. It became linearly separable in h1 and h2. Okay, these new features, we call them, become new computed features, correct? So the two ways we looked at, one is to incorporate this non-linearity or non-linear combinations of your input features. So we got the x1, x1 multiplied by x2, and or we did this computation in two stages. So when we did that, it actually made the problem a little bit more easier to solve, right? So because when we did this h1 and h2, we saw that the problem becomes linearly separable in h1 and h2. If we start with x1 and x2, compute h1 and h2. In h1, h2 space, the problem was linearly separable, right? Here it's linearly separable. Okay, so now we will get to the point where we are actually talking about feed-forward neural networks, right? So we looked at in the previous example where I showed the XOR gate. If we have one additional layer of Boolean operations of computations, then we can actually make the problem linearly separable in terms of the outputs of the intermediate computations. Okay, so that's exactly what a feed-forward neural network does. That it does layers of computations. Okay, and we'll see what those layers mean. Right? So feed-forward neural networks or multi-layer perceptrons. They are called MLPs. I think you must have come across this acronym somewhere. They perform a sequence of computations on inputs, right, and eventually map to an output. Typically, we'll only look at scalar outputs. Okay, so of course it's because it's a sequence of computations and there is no feedback. It's called a feed-forward network. Okay, and this is accomplished using a composition of different functions. Okay, and each function defines a layer of computations. Of course, we'll typically write it in this form. So you will have something like your input is f1 of x, and then this will be input. The output of this f1 of x will be given to another function f2. Okay, and the output of this f2 can be given to another function f3, so on and so forth, right? So this is actually a composition of functions. So this will be the input layer. It's called for the first layer would be called the input layer. The second layer, the intermediate layers are called the hidden layer. So input, hidden, and the outermost function you see there is your output layer. Okay, so this is a composition of functions that we apply, and each function is a layer. Okay, so we'll see how it's represented soon, but this is typically how you interpret a neural network, right? But of course, the computations you will do will be in sequence, and it will be done on discrete inputs. Okay, so all computations are done on discrete inputs. Even though I'm saying x here seems like a continuous variable, x is a discrete input. It's a vector of elements typically. Okay, so the inputs are always discrete, and the outputs of these functions also lead to discrete variables. We'll see how they come about shortly. So to summarize, the innermost function is the input layer. The outermost is the output layer, which produces your output, which is y hat, whatever this might be. We'll see what are the different types of outputs possible. The intermediate layers are also called the hidden layers or activations. We'll see why they are called activations. Now each of these layers, or we can treat them as a function, they are parameterized by weights w, and sometimes we use w's or theta, either is fine. and they are usually estimated like we did for a linear regression. They are actually also estimated using training data. The reason why we call them neural networks is because they are inspired by neuroscience, wherein the sequence of computations where we go from one layer to the other, starting from an input layer to an output layer, is how the neurons in the brain are connected. Okay, so it's inspired by that, but they are no means a very good model of how the neurons work. Okay, also to remember the so-called hidden layer, even though I say it's a function, they are actually vectors. So we'll see how that works out and why they are vectors in using a few examples. Okay, so for one hidden layer feed forward network, okay, the hidden layer is computed using the function. We'll see what that function is, and the values of the hidden layer, which is basically another vector, is used as input to the output layer, which eventually outputs only a linear function of the h of the hidden layer, and we treat that as the output, and then we do all sorts of training using that. Okay, now this kind of network is a composition of two functions. So let me illustrate that. So what we saw, especially for the XOR exclusive OR function, in terms of the OR gate and the NAND gate, is basically a one layer. You can think of it like a one layer neural network. But we'll see what these eventually translate to for in terms of algebraic operations. So let me just illustrate this with a small example here. So for instance, your inputs are still x1 and x2. Okay. So then you have these connections which go to another computation. Okay. You calculate h1. From there you have another set which goes to another computation. You can use black actually just to be consistent. So we'll do h2. Okay. All right. So let's we can of course always write down the output. This is the one layer network. So then take this and we calculate y hat. Okay. Now, what is the relationship between x1, x2, h1 and h2? Okay. So this is the hidden layer. This is the hidden layer. And why do we interpret this as a function? We'll see. Okay. So the way to calculate this hidden layer in a feed-forward neural network is the following. We'll first do just a linear combination, and then we'll see why it doesn't work, and then we'll go back and we'll include the non-linearity and we'll be able to understand. Okay. Now this red line, each of these red lines refer to a weight. So I'm going to write the formula here. This h1 is sum w transpose x. This is a vector. This w is a vector. And this is sum w transpose into x, where these blue w and red w are vectors, right? So these are weights, each of them unique, one set of weights which multiply x1 and x2 in order to calculate h1. These blues are another unique set of weights which multiply x1 and x2 and to get h2. So then we can write h1 h2 as right. So you have a red, I'm going to write this as a red column and a blue column of it. So this is a 2 cross 2 matrix. This is a 2 cross 1 vector that gives you a 2 cross 1. Okay. So that's why we have the input to every layer is a vector. Output is also a vector. Except for the last layer, which typically has well, sometimes it is a vector, but in the case of regression, it's going to be a scalar. Now, what about this layer here? Okay. So here too, once again, I'm going to multiply, pre-multiply, in this case, h1, h2, and I have a w, which is basically two weights. Okay. So I'm going to have a couple of weights here, and that will give you my y hat. Okay. So we'll call this. So what I'll do is I'm going to call this first layer matrix this as w1, The second layer matrix here I'm going to call W2, right, or W1 transpose, W2 transpose. So basically your output becomes W1 transpose, W2 transpose of X. Now if you think about it, it's still a linear model, still linear, okay, because W1 into W2 I can write it as another matrix, doesn't help. Okay, we are still in the linear regime. So typically, so what happens in the neural network is you would do a point-wise non-linearity. So we will see what that is immediately. I'm not going to. Let me just yes, produce the figure. But what I will do is, so typically what you will do, you have this matrix W1 transpose, your X's, right? This will give you a vector Z. Okay, so this will give you Z1, Z2. It's the output if you just do that. And you apply a pointwise non-linear function to this. What would be a good what would be a non-linear function? We will see. So basically, this will go from W1 transpose of X, W1 transpose of X times X will give you some Z. Then to Z you will apply G of Z, some function. Okay. Once again, I am kind of not indicating the bias term. So because this is still W1 transpose X is still linear, right? So we can always add a bias term. So W1 transpose X plus C. Okay, I'm using one bias term for all the weights. Okay, right? So that is your Z. So you would apply the non-linearity to the whole thing. So to G of Z. So which is nothing but G of W1 transpose X plus C. Okay. Similarly, at the output layer, you would also do that. From H1, H2, you might or might not want to do the non-linearity depending on what you are trying to estimate. Okay, the output layer is still a linear layer, right? Because you had, for instance, if you go back, so you had H1, H2. Let me add one more here. Okay, for the last layer, output layer, we had H1, H2, right? So you can actually just have some W2 transpose H that will give you your y hat. Okay, you can apply your non-linearity G of y hat eventually give you the y hat. So I won't call this y hat. So for instance, let me call a different name so that it's not confusing. So this W transpose H can be some Z hat. Then you would apply this Z hat to give your y hat. Okay, this can be done. So what is this G function? It's like I said, you have to apply it point by point. So for every H, so H1, so you would calculate G of H1, G of H2, right? That's you would do that, right? In this case, so the previous case, your output would come from every Z1 and Z2, right? We saw that. So what would be this ideal nonlinearity? The one that is often used these days is called the ReLU. ReLU is something. So if we have an input, in this case, I'm just going to call this Z. For positive values of Z, it's just identical to Z, 45-degree line. So I'm going to use blue so that green so that it's easy. For everything less than or equal to 0, you get 0. Okay. So you basically it's a function which reads max of 0, Z. Okay. So this function, so this is a non-linearity because it zeroes out all negative values and keeps only the positive values. So this is one of the simplest non-linearities it use. Apparently works really well for a lot of the problems that that come about these days as applications of neural network. So just to recap, the different layers in a feed-forward neural network cannot be just linear layers because then they can be combined into a one big linear model. The non-linearity is required so that the problem becomes linearly separable, or we can get extract features which make it linearly separable. So a linear combination followed by a point-wise non-linearity is what is typically used in the hidden layers, sorry, not lanes. So by point-wise non-linearity, we mean non-linearity is applied to every element of the hidden layer vector. Okay. The values that you get after applying the non-linearity to the to the affine transform, that is Z, is also referred to as hidden activations. Okay, here's how we summarize the computations in a neural network, right? Let's say we are looking at one hidden layer. How can we summarize its computations, right? So we have an input x. Okay, it's blue. X is some vector. Okay. So at the input layer, we are going to multiply this x with a weight matrix. So some W transpose x is what we are going to use. Okay. The dimensions of W depend on what the dimensionality of the output that you want. So this is a vector of dimension n. So we will be multiplying it with the matrix. So this x has dimensions n cross 1. Okay. So we are multiplying with W transpose. So W transpose should have dimension let's say p cross n, so that your output will be of dimension p cross 1. So this output, again, this is the hidden layer that we want. Hidden layer, the first step in the hidden layer, we call this Z vector. Of course, to each one of these elements here, we will apply the non-linearity, that is the function, non-linear function we saw, that is ReLU, and that will eventually give you the hidden layer activations. Okay. So each of this will have, I have p rows and n columns. So you would take one row and multiply it here. So an affine combinations of each time with different set of weights will give you as many hidden layer outputs, correct? So then we will take this capital W, I am going to call this W1 transpose X. So you will get this hidden layer H. Okay. Of course, I have left out always leave out the bias term, free to add it as B. You usually have, so in order to do that, you will actually have a 1 here, and then the leftmost column you will have the W0, okay, the weights, the bias term. But anyway, so in this case, let's say W transpose X plus B, or we'll use C instead, last one we use B. Then once you get the Z's, the Z vector, you apply point-wise non-linearity, and which will eventually give you your H. Okay. So now you will take H, multiplied with the second layer of weights plus C, and you will produce an output. Okay. Now in this case, depending on the problem, you can have different kinds of outputs. Okay. So once again, the dimensions of W2 will depend on what kind of outputs you are looking for, in the sense. So for instance, what is the dimensionality of output? So for instance, if you are doing a regression problem using a feed-forward network, it's just 1. Okay. So then you can adjust the output of size of W2 accordingly, right? You will have create as many weights. So this tells you that these weights, the number of weights that you have in every layer is a hyperparameter. So is the number of hidden units. So each of these elements of the hidden vector that you calculate is a hidden unit. So the number of hidden units in a neural network is also a hyperparameter, something that you have to decide based on the problem. And this number can be greater than or smaller than n. So your hidden unit, your input unit layer has n units, or n, it's a vector of length n. Then your hidden unit can be either smaller than number of elements or higher number of elements. Okay, that depends on the problem. So that is like a hyperparameter that you have to tune in order to solve this problem. Similarly, depending on the size of your output, you will have as many. In this case, if you want to think of it in terms of how we did this, you will have as many rows in this W2 matrix as there are outputs. Okay, so this is the typical construction, right? And what we don't know are the weights. So just to understand the problem, we don't know what W1 and W2 are. We would initialize them randomly and then estimate them using gradient descent. Because we have for every y hat, we have the corresponding y, and we can formulate an appropriate loss function. Okay. So for feed-forward neural network, there are two types of problems. One is the regression and in the classification problem. So for the regression problem, we will be outputting the target value y, we call this y hat, and then we can do a least squares loss. Okay. Now the advantage behind this, if you look at the neural network, you will see that you can actually output whatever value you want. Okay, you can output whatever value you want. You just have to assign it that meaning. Okay, in my case, I output y. Which in the y hat, which I say that is the same as the target value y for linear regression. Okay, but it could be some other parameter also from which I further calculate y hat. Okay, so that those things are possible with the feed-forward neural network. So for classification problem, the output should be a probability value. Okay, so if you are doing a two-class classification, right, then the output should be the parameter of the Bernoulli distribution. So we still call it P, but I'll call it let's say nu in this case, or mu also is fine sometimes. And what do we do? So because when we do W transpose, let's say W2 transpose H, and we get one output, it's a scalar, okay, and we don't know what to do with it, right? So the best way is to squash it. So people usually use this sigmoid function, the sigma of W2 transpose H plus the bias term, and this maps it to the interval 0 to 1. Okay, what is this sigmoid function? Sigmoid function we'll look at very briefly. So sigmoid function of x is basically 1 over 1 plus e to the minus x. Okay, so all it does is it will map your values between 0 and your input values between 0 and 1. So if you want to plot it, it's basically looking something like this. Okay, so 0, so negative values. Okay, this is positive values. Say this is z. Okay, the intermediate, the affine transform, that is basically the W transpose hidden plus the C, or W transpose X plus B. All of these are referred to as Z. This is the linear combination of your inputs, or the input to or any of the layers, right? So now you can Z, if you plot this sigmoid, it will be something like for so it's at this is at 0.5. Okay, at 0, if you get 0, you get 0.5, right? So for negative values, you get output less than 0.5. For positive values, you get greater than 0.5. Okay, so of course you can tweak that by the slope and all that by adding some fudge factor here, multiplying with some fudge factor here, but we won't get there into that issue. So we will be, for the output layer, we will do 1 over e raised to minus W transpose H plus C. This is what you would calculate. Okay, this is the sigmoid function that we will calculate, and this is what we will use to convert our output to a probability value between 0 and 1. So this is the case for two class classification. So then what do we do if we have? So what we did for a two class problem is we produced this output y hat, which is nothing but the probability that that the input given x, it belongs to class 1. Okay, so this is for a two class classification, right? So for for k classes, okay, so if for k classes we need this probability, it belongs to the ith class. Basically, this is what we want to figure out given your input vector, right? So I'm using small and large interchangeably. I will just use the x. Okay. So we need to produce as many outputs as there are. So if you have k classes, we're going to be evaluating these probabilities. So how do we do that, right? So we know that from the hidden layer, we have so many hidden vectors, the size of the vector in the hidden layer H. Then we have weights. Let's say we are doing 3 classes, right? Just want to show what we have to do for if you are doing 3 classes. Let's say 1, 2, 3, 4, 5. We have 5 components in the hidden layer vector. Then let's see if you want to do 3 different outcomes, right? we are looking at 3-class classification problem. So let's just do this. Red, right? So this will give you 1. So similarly, we have preview 2 and for the green. Okay. So you'll have 3, and this again, before you apply the non-linearity, you have Z for this is W transpose H plus some B. Okay. This is the Z you have. So of course, the W transpose is composed of, if you look at it in terms of a matrix, is composed of these 3 colors, right? Here, the middle one, 3 rows, right? And of course, I haven't specified the length of the H vector, so it's 5. So you'll have, each of them will have 5 components, right? So this will give you 3 outputs. This is Z and it's unnormalized. So then we have to convert that into a probability, right? Because usually the outcome is only one of them. So they are independent. So if there is only one, if one of the classes is probable, then the other 2 are not. Okay. So in that case, then the probability should add up to 1. And of course, they should all be in the range 0 to 1, and they should all add up to 1. So in this scenario, you will have is known as the softmax, right? So if you write this Z as equal to W transpose H plus your bias term, then your probability, to convert that into a probability, you will do this softmax of Z for every one of them, which will be nothing but exponential of Zi divided by summation over all the classes J. Okay. So there are K classes, J equal to 1 to, let's say, capital K, exponential of Zj. Zi, where does that come from? So if you have 3 classes, when you do W transpose H plus B, you will have Z1, Z2, Z3 here. Okay. So then you will have, so just to illustrate for one, the probability associated with class 1 would be exponential of Z1 divided by exponential of Z1 plus exponential of Z2 plus exponential of Z3. Again, you have to, for class 2, you have to change it to 2, 3, so on. Okay. So of course, you have to fix what each of these classes are. When you write the program, you say first element corresponds to class 1, second element corresponds to class 2, third element corresponds to class 3. Okay. So that's the output, and that's how we interpret the output. So if you want probability for one class, for a 2-class problem, you use the sigmoid and you interpret the output as the Bernoulli parameter, okay, which indicate the probability yes or no. Okay. And if you have a multi-class problem where, of course, the choice is one of k outcomes, right? One of k classes. Let's say one of 3 classes in our case, which we looked at. Then you calculate the softmax function using Z, using this formula right here, and treat those as the probability of the outcomes. Okay. So far, what you have looked at is the so-called forward pass through a fully connected neural network. Okay. We are also not defined fully connected yet. But we will get there. So what we have done is we have taken a vector of inputs. So each input data point is a vector, and then we have multiplied it by a matrix of weights to get this linear transformation of the inputs, and then that's also another vector. Then we have applied a non-linearity, point-wise non-linearity, each one of them, to get the so-called hidden layer or activation or hidden activations. We can do that sequentially as many times as you want. Finally, we estimate an output. The output can be either just the linear combination of the last hidden layer, which we call the output layer, where or the penultimate layer from which we estimate this y hat, which can be a real number if you are doing a regression problem, or it can be interpreted as you apply a sigmoid function and convert it into a Bernoulli parameter if you are doing a 2-class problem, that is yes or no kind of problem. or use the softmax function, convert that into a vector of probabilities, all of them adding up to 1, if you are looking at a 1 of k classification. Okay, so that's the idea behind the feed forward neural net.